All right, here we go. Back in the cylindrical and spherical coordinates. Cylindrical and spherical coordinates. Well, ultimately, the biggest warning I can give you is embrace the trig. Your trig has to be you got to be ready to trig. You got to be ready to trig when we do this. So any point on this circle can be described by... Oh, right, you might be thinking like x comma y, absolutely. But we're trying to get into cylindrical. Cylindrical is the 3D extension of polar. So polar, instead of thinking in x, y, well, I draw my radius or my distance. I know that the x component is cosine and the y component is sine. Dude, y'all, this is no different than our magnitude times cos theta sine theta. Like our vector work is no different than what we're doing right here. So if I want the coordinate, it would be r cos theta r sine theta. Oop. Where theta is the angle it makes with the axis. And thankfully, cylindrical coordinates are kind of nice. Not a whole lot to worry about. Cylindrical coordinates, just take it and add a z. I take this and I add height to it. I take this and I put it into the ground. That's all cylindrical coordinates are doing, is taking your polar and extending it into 3D. We are not doing the limacon, the heart-shaped things. So not worried about that. We are really focused on circular things. And so all sorts of things like pipes and turbines and things like that are well represented in cylindrical coordinates. When we're doing integrals inside of circles, when we're doing integrals inside of those types of shapes, it will be easier to integrate if I convert to cylindrical. Again, right? Why would I want to integrate this? Right? Why am I going to integrate this type of function? This is bad notation. Don't hate me. When I could just integrate this. You want to integrate this, so you actually want polar. You want cylindrical coordinates, so we get out of Cartesian yuckiness. And again, this memorize is going to save your life. You got to remember it. Just a quick moment here. If r is a constant, that means my radius is not changing. That means I'm dealing with a cylinder, just like we had in the last lesson. Whereas r is equal to z, that's kind of giving it a slope. That means as my height changes, my radius changes, and I end up with a cone. If I just threw one on Desmos 3D real quick for you, it would look like this. Right? As my height changes, my radius, my distance to the wall gets larger. All right. Back to this sheet we are. So my coordinate, instead of x, y, z, now goes r, theta, z. And the conversion is going to come from here. We know that theta comes from tan inverse. We did this already. We know that r is from the Pythagorean theorem, x squared plus y squared. Distance formula. And z is just z. So if I got a coordinate like this, which is cylindrical, and it says, hey, convert this thing to Cartesian, let's think about what this is. R equals 3 pi over 4. So I start on my x-axis, and I'm counting over past pi over 2 to 3 pi over 4. I'm heading out at a distance of 2. And then I'm sending this thing down 2 spaces. Okay, that's not impossible, right? You can find the x and y coordinates here and then add that z is -2. Like, thankfully, I already know in my answer, it's going to be comma -2. To go find those x and y values, I know that I'm going to use trig. Right, this is a triangle. Y'all, this is a triangle. doing a little cheat there. You can follow the formula if you need to, but I'm using a little cheat here where I know this is going to be 2 times each of these. I could put it in the right quadrant if I want to be a little more specific, right? But because the 3 pi over 4 is over here, hopefully I'm not losing you too fast. I know pi over 2 is rad 2 over 2, but it's twice that, so this turns into rad 2 and rad 2. Again, I could be doing this 2 times cosine 3 pi over 4, where you'd get negative rad 2. I could do 2 times sine 3 pi over 4, and I'd get positive rad 2. And that just builds my coordinate. Negative rad 2, positive rad 2, negative 2 would get me to this coordinate. Negative rad 2 this way, positive rad 2 this way, negative 2 that way, down. All right, convert from rectangular to cylindrical. So now I get my x, now I get my y, now I get my z. Right? If you want to go quickly, you can memorize and just start chucking this crap into your formula. Or you can be in that holistic knowledge. You can understand that this thing is back 1, back 3, up 2. Back 1, back square root 3, up 2. So it's somewhere up here. I know that my angle is now going to go past pi. I know that I'm going to be in the third quadrant of xy, but then up for my z. I know, thankfully, once again, it's going to be comma 2 because z stays z in this case, but to go get my radius, remember, I have a triangle here. Negative 1, negative rad 3. So I just go find that using the distance formula. R squared is negative 1 squared plus square root negative 3 squared. So then r squared is 4. So r is 2. The radius is really only positive. We don't want to mess with negative radius. It doesn't logically make sense. It's also not going to really produce the answer for us. So I got my positive r. Now I need the theta. I know it's 2 blank 2. Well, if I want to go find theta, I can do rise over run. But I do need to make sure it's placed in the right quadrant, right? My theta is that. So, again, I could kind of cosine it now that I know that this, right? This is when cosine equals negative 1 over 2. Okay, maybe that's too much. Maybe that's too much. So I'm going to go tan inverse of the rise over run, negative rad 3 over negative 1. And I'll pop out my answer on this one. I believe that is pause brain, more rise than run, that is a 60. But it's 60 past 180. It's a pi over 3 past 180. And so that's going to be 4 pi over 3. When you plug this in, you're going to get pi over 3 because tangent is going to be giving you the first quadrant equivalent, but you have to know you're in the third quadrant to get your third quadrant angle. Keeping on, keeping on. I don't want this thing to be too long. I've already spent 8 minutes on the easy half. Well, it says convert this following equation to cylindrical. All that means is everything has to only has r, theta, and z. This equation cannot have anything that's not r, theta, and z. And I'll admit, reading these equations when they're in this format, really don't tell me what the shape is, are harder to understand. So we know that rectangular coordinates, plain x, y, z coordinates, make us more comfortable with what we're doing, but the math might get easier by switching to an alternate coordinate system. And so that's what we're looking at. I know that x squared plus y squared is r squared, just like r is x plus y square rooted. Well, here I have 4x squared plus 4y squared, so that's going to make 4r squared. So that's the only change I have to make. 4r squared plus z squared is 1. Again, harder to read, harder to graph, but it only deals in r's, thetas, and z's. That's it. The reason I'd have a plane theta comes from that other relationship that I'm just going to write here. Don't forget it. X is r cos theta, y is r sine theta. So if I had any linear x terms, linear y terms, I would end up with thetas in there as well. Here we go. Now, we are getting into spherical. The first thing I'll say is my radius is no longer referred to as r, it's referred to as rho. It's like I have this big globe and I'm all the way out here on the surface of the globe trying to find a way to refer to it. I like to think of it in terms of like a sailor is on a ship here at the origin and he's looking up at the stars, which are sitting on a globe, right? Our sky is globe shaped, our sky is spherical. Ugh, our sky is spherical. So he's looking at a star up here going, well, if this star is here and this star is here, where is my course headed? How do I need to change my direction? That's always how I view it. There's other uses of spherical. Obviously, I said astronomy, space, but also longitude, latitude, geography, navigation, and also in terms of anything like speakers or magnets, those things emit in circular patterns often. So spherical coordinates are going to be the answer to that. So let's kind of get into our definitions here of what these things are. First and foremost, we still have theta, and this theta is still the same opening that we've had before. Again, from here, opening this direction to some angle, that's still my theta. That is unchanged. And I know that theta is still tan inverse of y over x. That's still true. But also, theta, like we found out before, is also related to r cos theta and r sine theta. So in different situations, I might be choosing these different things to represent. Or one piece of information might help me with some other pieces of information. Next, my rho is that radius which sticks out here, like if I built this thing to here. It's just a distance. But then, like if this sailor is looking at this angle to his right, left, if he's looking up this distance to the star, he's also thinking this way. How far am I looking up? And that's our phi. Whoa. So we have our side-to-side angle, and then we have our up-down angle from surface level, from eye level. He's either looking up or down. And so that's why I have this image here for phi, because phi is going to be your positive angle that you're looking up, or a negative angle that you're looking down. But phi always doesn't open from the plane of view. I lied a little bit when I said that. I lied a little bit as I drew these. Because in order for us to stay consistent, we're dropping that view down from the top. That's where we find phi. This is where we find phi. This is where we find phi. It'll make more sense as we get to examples. So phi is locked into this range between 0 and pi. I'm never going to look down and back around to get to this backside over here where you might be considering values of phi beyond pi, right? Things over here, things back here. I would just move my theta around and my phi would remain in these bounds. And then rho is just my radius. But let's do a little bit of trig to get this answer. I have my angle here, and I have my radius out here to this moment. We're going to keep drawing on this idea. So again, I know this coordinate is a little bit of y equals r cos theta, and then y equals r sine theta. I'm all over the place today, sorry about that. And x equals r cosine theta. But then I need to get this length, not this length. I need this length. So I need to bring that thing a little bit more vertical. Well, what I'm drawing here is a right triangle, where this is my z. So again, I have a new triangle. This is my radius away from my point of view. It's getting lifted up a z distance. And the hypotenuse is now my rho. So again, if I want to find rho, rho is z squared plus r squared. You also might view this as z squared plus x squared plus y squared, which we already saw was the equation of a sphere in our very first lesson of the year. Again, my rho can only be positive. Then down here with phi, I can build my phi again with some triangles, except that because that angle opens from the top, it gets a little bit funny. Right? Now it's like I'm building a new triangle here back to my z-axis. And here's my phi angle, here's another angle, and then my right angle comes in. I've fucking lost the plot. Damn it, 17 minutes wasted of my life, fuck.